Can we start? Yes. All right. Thank you very much. Then I guess I'll move this over or not. Okay, welcome guys. So I'm Marcel Dunaiski, and I've got two appointments. One is that I'm a lecturer in computer science, and the other one is I do research for the School of Data Science and Computational Thinking. I'll talk a bit about that later on. So what we'll be talking about today, the main topic is how one can use citations and citation networks to rank researches and papers within the citation network. So to get there, I quickly will talk about databases, so the data that we need in order to achieve that. Then I'll give you a crash course on citation metrics. And then we get to the main crux, and that is indirect citation metrics. Those of you that have heard of Markov Chains, they'll probably make it much easier to get that. But then, very field specific is how do we normalize the scores so that when we are comparing researchers across different fields and over time, so that we do a fair comparison between them. And then lastly, I'll try to get there. I have to talk very fast to get there. Evaluations. How do we make sure that the metrics that we design are actually doing what we want them to do, right? So, some terms first and where this started from. So I'm giving you a bit of a history lesson here. Bibliometrics started around the 1900s, and it started when librarians tried to figure out which journals to subscribe to put in the library because of them becoming more expensive. So they looked at citations, so they looked at the research output and counted citations to see which journals needed to be subscribed to. And then later on, a broader field developed, and that was scientometrics, where not only did you look at the research output, but also at research evaluation, research tools, the management of science, and then also the laws and policy decisions behind science. So looking at those dynamics. And then informatics, and this is the closest one related to maths, is where you actually look at the mathematical properties and laws that underpin the dynamics in science, right? So what I'll talk about is mostly informatics, but based on bibliometrics. And since the advent of the internet, a whole new dimension started popping up because suddenly science was distributed over the internet and so on. So then the field of cybermetrics started and basically took everything from the previous fields, but then researched the interrelationship between those and the internet. And more recently, altmetrics became a thing where not only did one look at citation and citation counts to evaluate research, but also things like sharing papers on Twitter. How often was your paper talked about in news media and so on. So that is called altmetrics, alternative metrics. Okay, quick, have you seen these? Google Scholar, Scopus, and so on. Stanford University subscribes to Scopus and Web of Science. So if you want to do citation analysis using this data, you'll have a hard time still, because even though you have a username with your Stanford University address, you're limited to very small data sets that you can download. I think it's 5,000 rows at a time. So it's relatively difficult. There are open data like Crossref, but they don't have the same coverage as Scopus and Web of Science. I did my research on Microsoft Academic, but a couple of months ago it was culled by Microsoft, so that database is no longer updated, unfortunately, because that was basically the easiest to get, because these others, if you wanted to get the copy of Scopus or Web of Science, you would have to spend R500,000 to use for a year. You know, nobody has that kind of money. The one that has the biggest coverage is Google Scholar, but they don't have any API, no access. You would have to crawl the web to get information to do citation analysis, but then you get into problems. You know these recaptcha puzzles that pop up to see whether you're a robot? That will be your biggest enemy if you want to do citation analysis using Google Scholar. So this is just an overview of the size and scope and what kind of data these databases contain. But take these numbers with a pinch of salt, because they change every day. Google Scholar indexes hundreds of thousands of new papers and dissertations every day. So yeah, I just want to put that out there for you guys. So now a quick crash course on citation metrics. So the one thing that I always like to highlight is that citation metrics are not the same as impact metrics. So a citation metrics predominantly uses the citation information to attach some kind of value to a paper or to an author or to a journal. On the other hand, an impact metric can define the impact in different ways. So, for example, you could create an impact metric that uses social media shares. So what are you measuring then? Probably popularity maybe, or controversiality, especially on Twitter, right? If it's shared multiple times, you're not really measuring the impact in a scientific sense. What does the number of downloads or clicks mean, you know? That is probably visibility or something like that that you're measuring. So that's not a citation metric, that is an impact metric that is defined differently. A very difficult impact metric to get right is societal impact, right? How do you measure that your paper was used to inform policy decisions in government, for example? Very difficult to measure. Normally you have to go and do surveys or something like that. But today I'm going to talk about citation metrics that are defined or used as impact metrics. Okay. Now, why is it difficult to get that right? The difficulty, there are lots of different reasons why it is difficult. The most obvious one is that the reference conventions between disciplines differ. So this graph shows the number of references at the end of papers. So in maths, which is the bottom green line, you can see has clearly fewest references per paper on average. And this is over the years. So even nowadays, there's a big difference between a maths paper and the steep one over here in brown. I think it's management science. It started really low, but now it's 70 references on average per paper, right? That obviously creates a difference in the citation potential in the field, right? So that is one of the big problems. Then, apologies for this horrible graph. I tried to find a new one. This is actually from my master's thesis. That's why the cutoff year is 2010. The other problem is that the output rate in the fields are different, right? It takes much longer to write a maths paper and get that published than, for example, incremental research on a clinical trial, for example. Often you have a clinical trial that goes over years, but you can publish 15 papers on that. So the output rate in the fields are different. Over here, I don't have maths in this data set. We didn't have maths. But the blue lines is chemistry and biology, and you can see the rate at which those fields publish is higher than maths, which is somewhere there at the bottom. Okay, so that was the second problem. The third problem is that the citation rate after you publish a paper differs between the fields. So in some fields, it takes much longer for your paper to get a significant amount of citations, which we call the citation peak, right? In others, the peak is relatively soon after you publish it, but then drops. So that's, for example, biology again. The blue line, it peaks relatively quickly and then goes down. In computer science, which is the black line, not the top one, but the second one, I think, it's a more gradual increase and then it stays there on top. Again, this data is not the best. Comes from my master's research. All right, I think that was it. So, to summarize these issues is that the citation distributions are generally skewed and very long tail. So, a lot of papers have 0 or 1 citations, and very difficult to distinguish how many more citations signifies an impact, a significant difference, right? So one way of solving this is to use percentile-based metrics. And there are 3 different ways, 3 different examples. The top one over here basically says, if your paper falls into the top 10% of papers, so according to citation counts, then it gets a score of 2, and otherwise a score of 1. And then this metric over here, the R6 metric, is a bit more famous or popular. It has 6 different scores. So if your paper falls into the top 1%, it gets a score of 6, the top 5% gets a score of 5, and so on. And the third one is just a straight up percentile metric, right? So according to each percentile bracket, you get assigned a score. But this doesn't really solve the problem that if your paper is in the 0th percentile or the 1st percentile, how to differentiate the papers within that bucket, right? And we'll get to that. Now, probably know this guy. Google Scholar has 3 citation metrics, right? So, one common way to get rid of this skewed distribution is to define a threshold over where you say, if your paper has more than these number of citations, we count it, otherwise we don't. And that is that I-10 index that Google Scholar lists. So basically, it sets the threshold at 10 citations, and then every paper that has more than 10 citations, you count. So this threshold is very low in this case, but measures that are defined in this way count the, it's basically a measure of excellence, right? Even if this excellence is 10 citations. So Albert Einstein has 371 papers with more than 10 citations. Now there's the H index as well. It's probably the most popular metric for authors. And what one can do at aggregated research units, so if you're not only trying to calculate a score for a paper, but a set of papers, so for an author, for example, an author's set of papers, or an institution's set of papers, instead of working with a single unit data unit, you are looking at distributions, right? So you can compare distributions now. And that is what the H index does, basically. You have the distribution of all the citation counts of some entity, researcher or what, and you're basically calculating the biggest square that you can fit into that distribution. So the H index is defined as H being the largest number such that there are H papers with each H citations, right? And then you get the value over there. Okay, so to summarize quickly, you can classify citation metrics in 2 buckets. The one is the size-dependent metric. So those compute the overall impact or productivity of a research unit, right? The more papers you write, the more citations you can get. That number never shrinks. Then you have size-independent metrics, where they usually compute the average impact of a paper within that research unit. So you take the total citation counts of all your papers and you divide by the number of papers that you have. The journal impact factor, which is used, unfortunately, still everywhere, is one of those size-independent metrics. It calculates the average number of citations that the papers within that journal receive. Just now we talked about the I-10 index that Google Scholar came up with. Remember, that was the number of papers that have more than 10 citations. So the more papers you publish and that start getting more than 10 citations, your score increases. Even, let's say you stopped publishing, your papers can still accrue more and more citations. So even though you're not being productive, your score can still rise. I don't know why I'm saying that, because that's not really the point I'm trying to make. The analogous version of the I-10 index is the proportion of highly cited papers. So basically, you calculate how many papers do you have overall, and then you count the ratio between the ones that have more than 10 citations and the ones that don't. So that's the size-independent version. Okay, before we get into indirect citation metrics, was that kind of clear? Was that fine? Okay, so once you start publishing, you start caring about these things in postgrad or even, yeah, probably in postgrad. So I think this is why you're here, right? Indirect citation metrics. They are based on the idea that one should not only look at the direct citations to a paper, but also the citation chains of where those citations come from. And that naturally becomes a recursive problem, how far to go in. And it was first proposed by Pinsky and Norin in 1976. And they used an indirect metric to calculate scores for journals, again, to decide which journals are actually the ones that the university is interested in, and so on. So the rationale is that you want to decide not only how many citations, but weight the citations that are going to your paper. So that is important, a citation from an important paper counts more than a citation from an unimportant paper. That kind of idea lay dormant for quite a while until the advent of the internet. So when Sergey Brin and Larry Page published the PageRank algorithm, which stole this idea basically, they just implemented it in a very clever way, that led to renewed interest in indirect citation metrics. Right? So the idea is you let random researchers, random searchers, what they call, onto this graph. They pick nodes at random, and then they randomly follow citations to new nodes, and so on. And you model that process, you simulate that process, until two things happen. Either you reach a dead end, so in citation networks that would be a paper that doesn't have any references, or the papers that it references don't exist or are not indexed, right? What happens then is that the random searcher chooses a new node to jump to at random, or no matter where in the process, with a certain probability, the random researcher chooses a new random paper or node to start a new search from. So here's a graph of 4 nodes, 4 papers, and to make sense of the one maths formula I'm going to show you today, we need to know what the in degree is, but you probably have covered this already in your classes. So the in degree is the number of edges that are connecting to a node. So for paper C over here, it has 2 citations, so the in degree is 2. The out degree of B is the number of references going out of the node. So the out degree of B is 1, it has 1 reference to paper C. And then we also need to know what the in neighborhood and the out neighborhoods are. So the in neighborhood of C are the papers that cite the paper C, which are A and B. and then the out degree are the papers that are referenced by a paper. So in this case, the out degree, the out neighborhood of A are the papers C and D. So with those definitions, that is the citation count. The citation count of the paper is the in degree, right? And if you just look at the in degree, the number of citations, you have these problems. So recently published papers that didn't have enough time yet to accrue a significant amount of citations, so it doesn't represent how impactful the paper really is. But that's also true for old papers. So papers published in 1970 or what, because the scientific community was smaller, there was less chance of the paper being cited then, right? So we have to normalize for those situations. And the important part, I guess, for this talk is we want to figure out how citations from highly cited papers can carry more information or more value than citations from less important papers. The last 2 points over here are a bit more controversial. You can think about that. Should a paper that is published in a prestigious journal like Nature, should a citation from that paper count more than a citation from a local conference? Not sure. And the last thing is that we obviously want to normalize over the different citation densities of the fields. Okay, so here's where PageRank comes in. It's defined over here. You've probably seen similar definitions before. But the two things that are important for citation networks specifically, and not the internet, well, to a lesser degree the internet, is the damping factor. So the damping factor controls how frequently the random surfers, or the random researchers, stop their search and pick a new node to begin a new search from. And the second one is the personalization vector. So do we bias these random researchers to start their new searches at more recently published papers? Do we bias them towards a certain field? There are different things we can do to influence the process, and which are, So I'm going to talk a bit about which are good approaches and which are bad. So, like I said, the damping factor alpha basically controls the average path length that the random researchers take when traversing the graph. When alpha moves towards 0, you have more random restarts, and that means that you're basically evening out the score distribution over the years, right? Because they choose new nodes at random. So the more they randomly choose nodes, the more you're evening out the score distribution. You can see that with the light gray line over here. This is with alpha 0.05. If alpha moves to 1, then more focus is placed on the underlying network structure. But the problem with citation networks are that once you publish a paper, you cannot change the reference list anymore. Right? It's out there, it's published. You cannot now cite a recently published paper. So there's this intrinsic time arrow into the past. The random surface cannot move to the future unless they do a teleportation step. So if you don't control for the damping factor, then the random researchers will start moving towards the old nodes in the citation graph and score those nodes more highly. And this is what you can see with the dark maroon lines over there. The bigger alpha gets, the more the average score is increased for the older nodes in the graph. And for comparison, the blue line is just the average score based on pure citations. All right. So it's very important that you calibrate this damping factor. For the internet, it doesn't really make that much of a difference. because websites are updated, hyperlinks are changed, and it's not one-directional. Yes. The damping factor also makes a very significant impact on the computation time. So on the y-axis here is the precision to which you want to compute the final result. With the Markov chain, that's a state-to-state distribution. And on the x-axis, you have the iterations, right? And you can see the bigger alpha gets, the longer, exponentially, kind of, it takes to reach the precision that you want. Okay, and the last thing about adapting PageRank for citation networks is the personalization vector. So the functions over here, this is the initial distribution where you place the random researchers, right? For the basic PageRank, this was 1 over n, which was uniform distribution. If you want to change that with the personalization vector, and to calculate the values based on something like that, it doesn't really matter. The example over here is just incorporates two things. Time decay, so the earlier or the more recent the paper was published, over here the higher the score, but in this example it's also multiplied by the impact factor of the journal. Obviously, if you have those scores and you want to distribute the random researchers, you'll have to normalize that as well, so that your distribution is sums up to 1. And the only thing that you need to do to update PageRank is multiply this term with the same normalized vector. So, right. I also listed author counts over here. So the idea there was, since there are papers that have multiple authors, right? And the idea there was the more authors there are on the paper, the more visible a paper would be, because their friends read the papers and so on. So we also experimented with that to see if that increases the performance of our metric. It didn't. Okay, now how are we with time? Okay, I'm racing through this, let's see. But then we can have some questions afterwards and we can discuss these things. Metric normalization. So once we have a score for every paper or every author in a graph, how do we normalize that across fields and disciplines? And the biggest difficulty is actually how to define the fields. How do you assign a paper to a specific field? Now, traditionally, a paper was published in a journal, well, still is now, but the journal was classified in a field, right? There was a journal of computational machine learning, whatever, that was classified into computer science. But the problem is that you also have journals that are multidisciplinary, right? You've got Nature or Science. Those are famous examples that publish a wide variety of subjects. So then when you start normalizing, you come up with all kinds of issues. And the bottom line is that, especially, let's say 20 years ago, the within-field citation density was significantly higher than the between-field citation density. So nowadays, it's getting, the difference is becoming less because science is becoming a bit more multidisciplinary, and also the author count on papers become bigger. So these densities still matter, they're still significantly different, but they're becoming less. So I'm just highlighting two weird, or two side effects, I think I call them. What happens if you have ill-defined fields? So let's assume we have a math paper A, and we normalize it based on its co-citation. So we take all the scores of the papers that it cites, that cite this paper, right? So we've got paper A, and it's cited by other maths papers only. So we want to normalize the score within maths. So let's assume that paper A has a high citation count compared to the other maths papers. When we normalize, it will have a relatively good score, but normalized. Now it gets a citation, a new citation, from a field that has an even higher citation density, right? Typically that's medical and health sciences. Now, we're including the average score of a different field with high citation density. So we're adding that to the denominator of the normalization function. What that can lead to is actually a decrease of paper A's score, even though it gained one more citation. So these are side effects that one has to keep in mind that can occur if you're normalizing in a not ideal way. Remember I talked about percentile normalization, where you convert the scores to percentile scores. If you were to normalize all the papers within journals separately, so you convert the citation scores within a journal to percentile scores, and then you start comparing journals, it's obviously also quite a bad idea, because now you're saying that the top paper in Nature has the same score as the top paper within a local conference or something like that, right? So these are very trivial examples of how things can go badly, but just wanted to highlight some. So it's a very difficult problem to get right. What makes it even more difficult is when you look at discipline levels, so maths, computer science, engineering, and so on, and you only draw conclusions on this high level, then you can ignore the heterogeneities in the subfields, right? But once you start trying to do citation analysis for the small subfields, then that just falls apart, right? Then you really need to look at more advanced normalization strategies. So the research currently goes in two directions on how to specify fields. The one is you look at the citation structure in a more holistic way, and then you identify clusters based on the citation network. And the other one is to use natural language processing, right? Where you look into the content of a paper and you model the field based on the title or the abstract or something like that. The problem with that is it's difficult to convince people that the output of a model like that is correct, right? So let's say someone gets a score and they're not happy with the score based on this machine learning model, then they will never accept that that is the score they should get, right? And say the metric that you came up with is nonsense. So that's kind of the difficulty why the scientific community still uses relatively bad metrics that we know have issues, but they're still being used for evaluation and hiring committees and whatnot. So it's a continuous struggle to get this right. Now we assume that we figured out how to normalize over fields. Normalizing over time is easier. But what we found is normalizing over calendar years or normal time is a bad idea. It is much better, you get better results if you normalize over a number of papers instead of time. So this example, let's say you want to calculate a score for the paper, the focal paper over there. You define an interval, but not in terms of time, but in terms of number of papers. And then you select the papers that were published most recently before and after that paper. So here's the formula on how to get those papers. You label all the papers, 0 to n, based on when they were published, and then you calculate the mean, standard deviation, and then you have a normalized score. Pretty straightforward. But the important thing is that you don't normalize over calendar years, because there are certain publication patterns that are make it so that it's not a good way of doing it. Yeah, if you only take the number of papers. So we use delta to be 1,000. So you look at 500 papers published afterwards and 500 before. You normalize within the field with those papers, and you get relatively good results. So let's quickly talk about the actual interesting thing, the evaluation. So we evaluated a couple of metrics. I'm only going to show PageRank and citation count here. We evaluated them across 2 dimensions: performance. So how good is the metric to actually do its job that it's intended to do? So if you are interested in impact, how well does it do that? And the other dimension is bias. How fair is it? How fairly does it assign scores across different disciplines and fields? Now, the problem with evaluating performance is that we don't have test data. We have no gold standard, especially for things like quality or visibility. Quality and significance. Quality is very subjective, right? You actually have to read a paper to make up your mind whether this is a good paper or not. Other things like impact or popularity are much more easy to calculate and evaluate. And this is especially difficult at lower research units, smaller research units. At institutional level, it's relatively easy to compare because you're looking at a lot of data that you normalize, so noise becomes background. But on the author level and paper level, you really quickly become, it becomes subjective very quickly. So what we did, we used proxy data. So there are different types of data that one can use as proxy for impact, for example. We used award data, so researchers that have won awards at societies or best paper awards at conferences, sometimes those are awarded at mostly computer science and engineering, but we found some other fields as well. Then there's survey data, but we never did that because that's expensive, especially because you're working on such a big scale. And the holy grail is peer review data. So in our F ratings, for example, F ratings are where peers review the standing of a researcher in South Africa, or journal review data. But those types of data is not accessible. Contains personalized information, personal information. So yeah, those are protected. You never really get access to them. Now the results. How do we calculate bias? It's very simple. We use a fairness test. So let's assume there's a sample of 100 papers. 80 of them are computer science, 20 are maths. A fair metric, this is our assumption, if we look at the top 10 papers, which have the same distribution, so there would be 8 computer science papers and 2 maths papers. Based on that, we can calculate a bias. So we've found that citations, using citations, is less biased in terms of time, but PageRank is less biased in terms of disciplines and fields. And then in terms of performance, we looked at 563 papers from 30 different organizations. And we used papers that were awarded a prize for their high impact. And this was, depending on the field, between 10 and 25 years after publication. So a selection committee came together, looked at what papers were published 10 years ago, and which of those papers made the biggest impact in the field. So we used that as test data to see whether PageRank and citation counts identify those papers accurately or not. And we found that PageRank always performs better. It's a red line over here, so the lower the better. But interestingly, we found that if you cut off the citation window, shortly after publication, the time normalized PageRank performs better, but after about 11 years, the non-normalized PageRank performs better. Of course, the random researchers going towards older papers makes sense intuitively. But the same is true for citation counts as well. Initially, the normalized citation count performs better, and then the non-normalized one performs better. All right. Here are some details I thought might be interesting. Ignore the first line. The second line I just talked about. When you personalize PageRank with citation counts, we found that the time bias is removed. We also found that PageRank's field bias is the least when you have uniform distribution. So any other thing that we tried didn't perform do better in terms of field bias. And that the damping factor influences the time bias, but not the field bias. And in terms of performance, PageRank generally performed the best with the damping factor set to 0.3, which is completely on the other side than what is good for the internet. The internet page of the damping factor should be 0.85, 0.8. Yeah, I think that's it. I was asked to quickly plug something here for the School of Data Science. I don't know whether you've heard of the School of Data Science. It's kind of a multidisciplinary school, but it has made significant impact already in the last 2 years since it started. We had the president over, we had the director of the World Health Organization over, and also in terms of cybersecurity, we were referenced recently. And here are some things that you might be interested in. So we have short courses, which mostly are for free if you're a Stellenbosch University student. So you can upskill programming, data science, statistics, anything like that. But also if you want to take part in a seminar in Venice this year that covers digital citizenship, we have funding for you guys to go over there. So follow those links if you want to. Cool, that was it. Thanks. So that was a lot of information. Do you have some questions? Please.
The question I had, so with regards to measuring the time as a delta in terms of like papers released rather than years, would that be because fields have times that are dead, sort of, where there's nothing coming out, but then all of a sudden a Higgs boson gets detected, and then all of a sudden you get this burst of physics papers?
Yes, that's one of the reasons. Yeah.
Okay.
Also, there are, it's kind of publication hedging, so you wait for a good time to publish your paper and stuff like that.
Okay.
There are lots of dynamics. We don't really know exactly what it is. There's still research going on, but in general, if you use the number of papers instead of months or weeks or years, you get a much more evenly distributed score.
And then another one, the damping factor being lower with the sort of in relation to like maybe an instant, would that likely be to that older papers don't reference newer papers?
Yes. Yeah.
So if you give the server too much time, it just ends up going to the 1960s every single time.
Yeah, exactly. Yeah, that's the main takeaway. And that was only relatively recently figured out because there was not much research being done until PageRank came around. Yeah.
Can you say a little something about the cheaters?
The cheaters?
Yes, the guys who game the system.
Oh, right.
They set up these citation fleets and whatnot.
Yes, that is a big problem. I didn't personally do research on that. What I did look into is how do you assign scores to the authors, so first author, second author, and so on. How to identify those citation loops on the author graph, I didn't really look into. Yeah.
I think that's an interesting problem.
Yeah, true.
I think if papers start citing, if authors start citing each other, there should be an exponential factor decrease.
Yes.
Somewhere there.
Yeah.
There's another factor, especially in math, and that is you have two papers. One takes an enormous amount of technical work to do in that field, and there's another paper with fairly easy math. Second one is going to get far more citations because more people can understand it and do, well, I can outgo it. Whereas this one requires, enormous inputs of time. So that makes this whole citation business very, very complicated.
Yep, that's very true. And there are many things that are very unique to to certain disciplines, right? And for ideal metric, which I don't think ever will exist, one would have to incorporate all these various intricacies in all the different fields. For example, high energy physics is known to have, what's it called? Not only multi-author paper, but I forgot the name, but you have papers that have over 1,000 or 2,000 authors on them. How do you share the credit of the paper among the authors? Do they all get the same credit, or in order to compare those authors to other authors in different fields, you would have to share the credit of that, divide the credit actually among the 1,000 authors. Yeah, there are all kinds of subtleties. But PageRank is usually a good starting point to get rid of those major discrepancies.
Are there all problems relating to, like, maybe somebody's written a paper that wasn't that popular. However, someone else then used it as a very big like cornerstone or rock that they put their paper on, which then becomes very popular. But that person who had a very big part of it doesn't really get too much recognition for what they.
That's exactly where PageRank solves it, actually, because the random researchers will always move to that initial fundamental paper. If you only look at citation counts, then obviously the second paper will get all the glory. Yeah. So, and that's the obvious one.
So the surfer that always clicks on it makes sure that they get that recognition.
Exactly.
In terms of like ranking the authors and things, how worried should one be about like having a suboptimal paper published at the beginning of one's like research career? like should you just try and publish as many papers as you, or is this like kind of unrelated to the?
Just in terms of metrics, well, if you look at a size-independent metric, you don't want to have bad papers in your collection of papers. But you never know when you publish it. You always think you have a great paper on your hands, and then you'll know whether it's picked up by the community or not. So, I don't know, my advice would be always try to write well papers and publish them as early as possible.
Yeah.
Yeah. Yes?
I think you mentioned like discussing metrics in terms of authors. Can you maybe say a word on metrics of journals as well?
So yes, so this is all based on my master's and PhD work, which is a while ago. I had dedicated chapters for the creating an author and then running PageRank on the author graph. I never looked at journals because there was no test data available, right? How do you subjectively, unless you ask researchers in the field which are the best journals, you publish them, you don't have test data. We didn't have a proxy for journals. A colleague though, in University of Washington, in Seattle, he and his colleagues came up with the eigenfactor metric, which uses PageRank like, well, they use PageRank out of the box, but with a very well normalized citation graph, where the nodes are journals and the edges are cross citations between the journals. And that, if you do that, so if you collapse the paper citation graph into a journal citation graph, suddenly you don't have that time arrow anymore, right? Because there are new papers being published in the journal that cite old ones, and collapsing those. So they also found that using PageRank on the journal graph especially works better than just journal impact factor, significantly. On the paper level, PageRank just minimally outperforms the citation counts like I showed today. On the author graph, more so, but on the journal graph, even more so. But because it becomes complicated, people don't understand how the value is calculated, it hasn't seen any adoption in the public, unfortunately. The website is still up, eigenfactor.org. If you really want to get an indicator of how good a journal is, I would suggest going there. Yeah. Cool. Thanks a lot.
So essentially, the best solutions are the ones that almost no one wants.
Yeah, it is like that. Can I reflect this? Yeah. Good question.
Ja, oké, maar is dat geslaagd? Dus ik kan het niet even.
I'll send it to Damien.
Was er links online?
Sorry. He asked for the slides. Is it fine if I